Good afternoon, good evening, good morning, ladies and gentlemen. Welcome to Tutorials with me, Aubrey. Now, in this lesson, we look at a very interesting concept in probability, and I hope you enjoy the lesson. I would urge you that even as we start this lesson, you subscribe to the YouTube channel and give us a like, give us a share. I am also urging you to rotate your phones to landscape mode because I observe that many people usually watch videos uh, in portrait mode, which many videos are meant for landscape mode, such as this one. So it will help you view the video much better, give you more details to video. So let's dive into this. So we look at the Poisson distribution. Poisson distribution, very interesting concept. Now, this distribution specifically comes from the binomial distribution, or the variables that we've been doing in the binomial distribution can be done, but even better, right? So the Poisson distribution helps us calculate um, probabilities for events that have many trials. Say maybe you've had you're doing an experiment of successes and failures, all right? Then maybe you trial those experiments for 500 times. Then someone asks you that in, let's say, 65 trials, what is the probability of getting a success or a fail, right? So it will be tedious for you to calculate the probability of getting the first trial plus probability of getting the two trial, second, third, and all the way adding to 60 trial. So the Poisson distribution can help us calculate the, the, the probability of many trials, because we don't need to know the total number of trials that are happening. Rather, we just need to know the mean of the trial, right? And the other thing that we need to consider is we need to make sure that the events that we're talking about, or the events that are happening in a certain framework, are independent, right? So those are the condition. Those are the conditions for working out Poisson distribution. Events needs to be independent. Then we're assuming that the mean is constant. All right, so we are assuming that the mean is constant. By the mean being constant, we mean, say we find the mean of 50 items, all right? The mean of 50 items, let's say the mean of 50 items, you know those proportions that we used to do? So if we find the mean of 50 items to be equals to A, we can easily find the mean of 70 items by simply cross multiplying. That is what we mean by the mean being constant. Right? The mean uh, is constant, right? So now, having said that, I think this is actually basically what you mostly need to know about the Poisson distribution. So the mean should be constant, the events should be independent. Let's also look at the, the probability density function we're going to use, all right? So the probability density function for Poisson is x, the probability of an item we're talking about, which is this x, is equal to lambda, which is the mean. So lambda is the mean of those events, the mean to the power, the probability that we're talking about, which is x, times e the power negative lambda all over x factorial. So lambda is just the mean, the mean that we talked about. So now I think the best approach for us to understand Poisson distribution is by looking at an example, because I'll be explaining more of the things from the examples that we're going to be looking at. So Let's dive into an example. So let's try out this question. So a botanist suggests that the number of a particular variety of weed growing in a meadow can be modeled by a Poisson distribution. So write down two conditions that must apply for this model to be applicable. So those are the conditions that we've talked about previously. So first of all, we need to assume that the events independent. Then secondly, we need to assume that the mean is constant. So this first question is already answered. Right, so now we go on to the second question. Assuming this model has a mean of 0.7 weeds per meter squared. Per meter squared, we are saying per one area, okay? Meter squared, okay? So this is very important. So we write down, so this is the mean, right? So the mean that we've been given is can use this or lambda. So I'll be interchanging because I'm used with mu. So the mean we have been given is 0.7, which is equals to 1 meter squared. So you should be able to interpret the data in this form. So 0.7 in 1 meter squared squared, right? So this is the mean that we've been given, right? So the probability that in a randomly chosen plot of 4 meters squared, so we need to find the mean in 4 meters squared, right? So what would be the mean in 4 meters squared? So we just need to make an approximation. So if 0.7, okay, is equal to 1 meter squared, okay, what will be 4 meter squared? So what would be the mean in 4 meters squared? I think I should just use lambda here instead of mu. Okay. Lambda. Okay. So we calibrate the mean according to the question, right? Using the given sequence. So what would be the mean in 4 meters squared? So it's just cross multiplication here, which is lambda times 1, which is just lambda. Then this times that. So in 4, our lambda will be 2.8, right? So now, what is the probability of the plot size, this, that there will be fewer than 3 of the weeds? 3 of the weeds, fewer than, so less than, fewer than 3 of the weeds. 3 of the weeds. So this is how we're going to calculate this. So let me just switch to my writing. All right, so I've just written down my data. So the mean is that one, 2.8, and we're asked to find the probability of fewer than 3, which is x less than 3. So x less than 3, we are just talking about the probability of x is 1. Okay, probability of x is 1 plus, actually we start from 0. Probability of x is 0 plus probability of x is 1. Okay, plus probability of x being 2, right? And we know that the probability of x is given by lambda to the x e to the negative lambda all over x factorial. So we just plug in there. So we always start from 0, 1, so on and so forth. So probability, now x is 0. So we'll just, let me just expand. Okay. Probability of x being 0. So we are putting in the formula here. We're using formula here. So x being 0, that would be lambda, which is 2.8, the power 0 times e to the negative 2.8 over 0 factorial plus when x is 1, so we put in, so it will be 2.8, which is our lambda, 2.8 to the power 1 times e to the negative 2.8 divide by 1 factorial plus when x is 2, which is 2.8 the power 2 times e to the negative 2.8 over 2 factorial. So basically we're just plugging into this formula right here. We're just plugging into this formula right here. So, should let me just punching in your calculator and all that. So let's do that. So when you punch 2 point, so this is just e 0 2.8 to the power 0, that is just 1, then e to the negative 2.8, right? So that is e to the negative 2.8 0.0601 times 2.8 to the power 0, that is 1, and 0 factorial is 1, so over 1 is just the number itself. So here it would be 2.8 to the power 1, which is just 2.8 times e to the negative 2.8 over 1 factorial. 1 factorial is 1 again. So that will give us times 2.8 is giving us 0.170268 plus, again here, 2.8 squared, that is 7.84 times e to the negative 2.8 times e power negative 2.8 is 0.47671. Divide by 2 factorial. 2 factorial, 2 times 1, which is 2. Just divide by 2, which is 0.2837, so on and so forth. So now what you just do is just add all this up. So basically that will be answer there. So that will be answer there, 0.465. All right, so that is the probability of that. So you can just go through for more examples in the next video.